100 trillion. Just look at that number for a second. It's kind of hard to even wrap your head around, right? It's more than 1,000,000 times the number of stars in our entire galaxy. And yet, that is the estimated number of connections, or synapses, that are packed inside a single human brain. Your brain, my brain. Every single thought you have, every memory, every movement, it's all happening because of signals firing across this unbelievably complex network. So, that brings up the big question for today. In this massive biological computer that we all carry around, how does a message get from point A to point B across even one of those tiny connections? Well, let's find out. Okay, our story starts with a main character, the star of the show, the neuron. This is the brain's fundamental communication cell. To get how the message works, we first have to get to know the messenger. So, a neuron is built for one thing, talking. It has three main parts. First, you've got the dendrites. Think of them like these bushy antennas, always listening and catching signals from other neurons. Then you have the cell body, the soma, which is like the command center. It keeps the whole operation running. And finally, there's the axon. This long cable is the transmitter, shooting the message out to the next neuron down the line. And if we zoom in even closer on those dendrites, you see these amazing little bumps called dendritic spines. These are like super specialized antennas, each one tuned to grab a very specific signal. This is where the real nitty-gritty of communication is happening. So, how does a neuron actually get ready to send a signal? Well, before it can fire, it has to charge up. You can think of a neuron that's just waiting around as a tiny biological battery, holding on to a little bit of stored electrical energy. The secret to this battery is all about creating a very specific imbalance of charged particles, which are called ions. So, as you can see here, inside the neuron, you've got a ton of potassium, but on the outside, it's mostly sodium and chloride. It's this careful separation of charges that gives the neuron the potential to fire off an electrical signal. And here's what happens because of that imbalance. The cell membrane lets just a few of those positive potassium ions leak out. And what that does is it leaves the inside of the cell with a net negative charge. And there you have it, a stored electrical potential. We call it the resting potential. Our battery is officially charged up and ready for action. But what keeps this battery from just running down? Well, it's this incredible little molecular machine called the sodium-potassium pump. It's like a tiny, tireless bouncer at the cell's door. It's constantly burning energy to kick 3 sodium ions out for every 2 potassium ions it lets in. This little engine never stops, and it makes sure that the neuron is always primed and ready to fire. All right, now for the main event. We've got our charged-up neuron just waiting. So let's see what happens when it gets a signal that's strong enough to push it right over the edge. This is the moment it fires. This is the action potential. So how does this charged battery actually fire? Well, forget about a slow, gentle discharge. We're talking about a sudden, dramatic, and explosive release of energy. The instant it fires, the charge inside the neuron just completely flips. In a fraction of a millisecond, the voltage skyrockets from its resting state of negative 70 millivolts all the way up toward positive 58. It's a massive electrical spike. And that spike, that's the action potential. And what's really wild is that it's an all-or-none event. The neuron doesn't have a volume dial. It doesn't whisper or shout. It just fires. If the incoming signal is strong enough to cross a certain threshold, boom, you get the full spike. If it's not, nothing happens. It's a perfect 1 or a 0. So what's the secret behind this electrical explosion? It all comes down to these highly specialized little molecular gates called ion channels. The second they sense that initial voltage change, the gates for sodium just snap open. And because there's so much more sodium on the outside, it just floods into the cell, causing that massive, rapid flip in charge. Okay, so we've lit the fuse. The spark has been created at the top of the axon. But how in the world does that signal travel, sometimes over really long distances, without just fizzling out? The answer is actually pretty brilliant. Insulation. A lot of axons are wrapped in this fatty layer called the myelin sheath. It works just like the plastic coating on an electrical wire. It stops the current from leaking out and forces the signal to literally jump from one gap in the myelin to the next. This makes the signal incredibly fast and efficient. So after racing down the axon at incredible speed, the signal finally reaches the end of the line, the synapse. And this is that microscopic gap between two neurons. Now it has a totally new problem. To get across this gap, the electrical message has to transform into a chemical one.
We've just gone through this incredible microscopic dance of ions and gates and charges. But why does it matter? I mean, so what? Well, it matters because when these tiny little molecular parts don't work just right, the consequences can be huge. We now have a whole class of disorders called channelopathies, which are basically diseases caused by faulty ion channels. And just look at this list. They're responsible for a really shocking range of conditions. We're talking severe epilepsy, movement disorders, even life-threatening heart conditions. It just goes to show how fundamental this electrical signaling really is.
And this is where it gets absolutely fascinating. The exact same ion channels are often the target of both deadly poisons and life-saving medicines. The toxin from a pufferfish, for instance, is fatal because it blocks sodium channels and causes paralysis. But a local anesthetic like lidocaine, it works by doing the exact same thing, blocking those same sodium channels, just in a very controlled way to stop pain signals. The source material we're looking at really puts it bluntly. A disruption of this flow of ions can be fatal. That one sentence just drives home the fact that a life or death balancing act is being performed by these tiny channels every single millisecond of our lives.
Which really leaves us with one final big question. We've seen that these tiny molecular gates hold the power over everything from thought to movement to life itself. So what's the next frontier? What happens when we get even better at controlling them to treat things like pain, mental illness, and neurological disease?